First, an announcement. Tomorrow night at 7 p.m. in Kruger Center, room 200, otherwise known as the amphitheater, or more accurately, an auditorium. Dr. Suzanne Phillips, who I just learned is a near relative of Abigail's. She is the chair of the Department of Earth and Biological Sciences at Loma Linda University, which is a segment of the medical school because, well, obviously, geology is part of medicine, right? They have an odd arrangement of their divisions there. But she will be here. She's an alumna of Union College. And just to make sure people speak the same English I do, alumna means a female graduate. Alumnus is a male graduate. Alumni is a group of male graduates. Alumni is a group of female graduates. And if you have mixed gender, you use the masculine. So alumni is also used for mixed gender graduates. So she's an alumna of Union College. And she will be giving a lecture. This is required for people like Noah and Christian as part of their class. But I hope that other people will come because she's going to be talking about belief in a world of doubt, belief in the Bible and what the Bible tells us in a scientific world where there is a lot of skepticism about the Bible. So I'm really looking forward to this talk, and I hope you'll come and enjoy it too. That is our announcement for today. Oh, yes, I should mention Christian and Noah, along with 4 of their best friends. Well, Christian, Noah, and Ashley are going to be defending catastrophism. Actually, they're not defending. They're presenting catastrophism this afternoon at 2 p.m. in this classroom as the reasonable explanation for the geological record. And their much hated enemies, Nathan Kanarski, Aaron Johnson, and McLean Kuho, is that how I'm saying it? Will be arguing against them in the debate, saying that no, it is uniformitarianism that is the best explanation. This is the first of 2 rounds. They'll have the same teams and the same topics, except the next round it will be the team on uniformitarianism will be presenting theirs as the correct answer, and the catastrophist team will be rebuking them. Question? So
you're going to be nice about this. Can we get extra credit if we go to the presentation tomorrow night?
No. I know I want to encourage people to come, but I think that is a misuse of extra credit. I know there are other people with different ideas. Like I received a request to give extra credit for a student for something that has nothing to do with the class because, well, it's a good academic endeavor. I don't think that's appropriate.
Well, we don't get any extra credit other than attendance in this class, so I would say maybe that would help to raise our grade.
Yeah, but it's non-germane, which makes it just making a travesty of the physics. It's like having double and triple worship credits for worship service. It's making a travesty of the entire worship credit system.
So what you're saying is you would come up with another assignment to the extra credit that's physics related.
Mm-hmm.
All right, don't forget.
Don't forget. Corso works the angles. You had a question back there, James? No, okay, I thought you did. Did somebody else have a question? All right.
I needed that.
I will be looking forward to Corso bringing up extra, hey, can I get extra credit for, if Man City wins the Champions League?
That one I'm getting.
Yeah. Anyway, just to make sure people besides Alex know, if Man City wins this next weekend against Manchester United, they will win the European Premier League soccer championship. Just so you know. I've been a long-suffering fan for, 4 years, while they've spent more money than anyone else and haven't won jack, so it's time. X-ray production is where we ended last class period. We talked about the Bremsstrahlung. The Bremsstrahlung is the whale-shaped figure there. I always like the wavelength version. This is a wavelength version showing X-ray spectra. And to me, this looks like a whale. And that there is the continuous spectrum the Bremsstrahlung. And the Bremsstrahlung, German for Breaking radiation is the radiation produced when you have acceleration of the charged particles. Because you're firing electrons at a high rate of speed into your sample, they're either losing speed, i.e. breaking, or changing direction to give off that radiation. And so the maximum energy you can have for that Bremsstrahlung radiation, you are making photons, right? Because this is light. And so the photon here, energy max, oh boy, I can't read that, and I'm the one who writing it. Energy max is equal to hf max, but since frequency is speed of light over wavelength, then that's also equal to hc over wavelength min. So that corresponds to all of the energy of the electron is converted into one photon. You're not going to have any light coming out with higher energy than the energy of the electrons coming in. So that's why you have that cutoff there. And then you see that the intensity of light is building up because it's much more likely that you don't have all of the energy emitted at one time. That's going to be emitted slower, that it breaks over time. And that's what gives you that Bremsstrahlung radiation. This graph here is showing the frequency version of it. Notice it's frequency on the x-axis. And on this one, you have a straight line on that leading edge that is energy converted into, just using the same idea, energy max. That was weird. Energy max is H frequency max. So they're giving you the same information. The graphs look a little different because of the axes they're on. Now, I did not check the textbook this week, but 2 years ago, I tried to correct the textbook because they have their figure in the textbook for the X-ray emission is wrong. It has the shape of, I can't remember if it's the shape of frequency, it has marked wavelength on the x-axis or the other way around. But they at least used to have a graphic that was incorrect there. So just be aware, these are what the picture should look like in case the textbook has a different picture there. So we've talked about the main part. What's causing it? Just electrons slowing down or changing direction. But what about these characteristic peaks? Called line spectrum in one of the figures and characteristic peaks in the other. What's causing that? Now you guys have all done reading quiz questions on this, right? No? Did anybody have a question asking them on that, or did you read and look at what's causing those characteristic peaks? Here's a tip. Notice those pictures aren't the same. One has two sets and one has one set. It depends on what metal the electrons are striking, what those characteristic peaks are. Hence the term characteristic peaks. It tells you about the metal. And what those are the result of electrons in your metal being excited. So something we haven't talked about yet. If you look at an atom, you have the ground state energy. So this is, we'll just put n equals 1. We're going to go with a very simplistic model. N equals 1 has the ground state energy. And then you have n equals 2, n equals 3, n equals 4, and so on. You have different energy levels that electrons in an atom can have. And when the high energy electrons come in, they can come in. High energy electron is going to look like this. And they can collide with an electron and make that electron jump up to, here I made it jump up to n equals 4. Well, now there's a vacancy in the n equals 1. And you guys have all had enough chemistry, you know the electrons want to be in the lowest energy state possible. So if there's a vacancy in n equals 1, some electron's going to fall into it. And when that electron falls into it, it's going to then give off an energy equal to the difference in the two energy states. So if I have an electron that falls from here to here, it's going to give off a photon which is going to be energy 2 minus energy 1, actually. So the energy of that photon is going to be equal to the energy difference for the electron that dropped in. And that energy of the photon produced when the electron falls to lower state, that's what's creating the characteristic peaks. And so these characteristic peaks are named. And the names of these characteristic peaks are things like K alpha, K beta, L alpha, L beta. Do the letters K and L mean anything to you from your chemistry? The what? Okay, that's what they are. The K is associated with n equals 1, and L is associated with n equals 2. And so K alpha means that the electron is falling into the K shell. It's falling into n equals 1. So K alpha is falling to n equals 1. K beta is falling into n equals 1. What's the difference in alpha and beta? Alpha means that it's a difference. Alpha is the first letter in the Greek alphabet. Alpha means it's a difference of 1. So K alpha means it's going from n equals 2 to n equals 1. No other way to read it. K alpha is going from n equals 2 to n equals 1. K beta, beta is the second letter, so that's going from n equals 3 to n equals 1. So which is more energy, a K alpha or a K beta? The beta is the bigger energy because it's a bigger jump in the gaps. Now, where are the gaps bigger, going down to n equals 1 or L, which is going down to n equals 2? Is your gap going to be bigger if you jump 1 going from 3 to 2 or jump 1 going from 2 to 1? You can just look at my picture. Which is a bigger gap, 3 to 2 or 2 to 1? 2 to 1. So that means that falling into the K is going to be a bigger energy. So more energy this way. So we can use that to label these. This only has 2. This is going to be K beta and K alpha. This one here, notice this is high energy on this side for wavelength. On the frequency, since energy is equal to HF, this is high energy on this side. So you have to pay attention. It's going to flip where they are. So the biggest energy here is going to be the K beta, then the K alpha, and then this is going to be L beta and L alpha. So I can label them by knowing what those labels mean and how the energies are going to compare. So that's our characteristic peaks in X-rays. Now, we've been talking about X-rays. Are X-rays a wave nature or a particle nature phenomenon? They're both light. Wave nature of light or particle nature of light. Are X-rays a wave nature or particle nature phenomenon? Particle. That's the correct answer. Why is that the correct answer? Okay, it's based on the energy of a photon. Anytime you invoke the word photon, it's got to be particle. Right? So the energy of photon HF was what we used to calculate the energies here. That means it's looking at specifically a particle nature of light, not a wave nature of light. In your experiment yesterday, you did the photoelectric effect. You were testing to see if that was going to support the wave nature or the particle nature. Which one did it support? It supported the particle nature. You should have had 2 outcomes. One is, as you increase the frequency, what happened to the stopping potential, the magnitude of the stopping potential? Well, as you As you increase the frequency, that's decreasing the wavelength. So as you increase the frequency, as you go to shorter wavelengths, what happens to the stopping potential? It went up. And so it went up linearly. If it goes up linearly, that should then support the particle theory of light, saying that the energy that's being absorbed by these electrons is proportional to the frequency of the light. And then you looked at intensity. How did intensity vary? You actually, wasn't intensity. I need to rewrite this part. It was the power that you varied. You varied the power by a magnitude of 16. You had your initial power, you had 4 times that power, and you had 16 times your initial power. What happened to the stopping potential when you went from your initial power to 16 times your initial power? Did it change? It actually should have changed a small amount. The reason it changed a small amount was because the equivalent is not perfect. You have the voltage goes up, and then it starts dropping down. And if you have lower intensity, it drops down more before it jumps up again. And so the average drops a little bit. With higher intensity, it doesn't have enough time to drop much, and it stays close to its peak. So the higher intensity is actually more realistic for your measurements, but that's an equipment failure. Or not a failure, but not being ideal. Now, when I was going through homework this morning with the student, we got to an equation where we needed to calculate going from frequency, I think it was, to energy in electron volts. Or no, it was going from wavelength to energy in electron volts. So for a photon, energy is HF. Planck's equation, that's your go-to equation. But then if you use the equation that F is equal to C over lambda, you can extend that to say, well, energy is also HC over lambda. You look up in a text and you'll find that H is equal to 6.62607, because we looked it up this morning, times 10 to the minus 34 joules times seconds. Now that's in units of joules times seconds. Those are our standard SI units. But we could have put it in electron volts times seconds as well. That's just going to use a conversion factor. What's the conversion factor between a joule and an electron volt? The charge of an electron. I can take this and divide it by 1.602 times 10 to the minus 19 coulombs per electron. And that will give me, when I do that division, the answer in electron volts times seconds. Well, if you take that H, convert it into electron volts times seconds, and multiply it by the speed of light, it will give you 1240 nanometers times electron volts. That's a really useful number to memorize. That number is actually not going to be given on the test, but if you have it memorized, that's fine and dandy. That number you simply get by converting H into electron volts and then multiplying by the speed of light. So it's easily derivable. But that makes life really easy, because you can say the energy of a photon is equal to 1240 nanometers times electron volts divided by the wavelength. So if I have a wavelength, this just take as an example research I was doing in graduate school. I used a wavelength equals to 248 nanometers. What was the energy of a single photon of that light? How much? So I was dealing with 5 electron volt photons. I calculated that 5 electron volt photons and talked about it a lot because I was studying absorption of light If I'm coming in with 5 electron volt photons, that light can only be absorbed if an electron can go from where it is to an allowed energy state that's 5 electron volts higher. I was working with wide band gap dielectrics, things that have a band between where the electrons are and the next allowed state that's bigger than 5 electron volts. So what should happen to my 5 electron volt photon if it goes through and no electrons can jump up by 5 volts, 5 electron volts? What's the photon going to do? It just keeps going through because it cannot be absorbed. And so that's what makes materials transparent. Glass is transparent because the electrons have a band gap, a gap between the energy state they're in and the next energy state available to them that's bigger than the energy of visible light. So let's look at the visible light. Visible light has about 400 nanometers as its cutoff. So for visible light, if we put in 400 nanometers for the highest frequency or shortest wavelength, how many electron volts do we have for the band gap for visible light? It's how much? 3.81. So visible light has its highest energy of 3.1 electron volts. If you have a dielectric with a band gap that's bigger than 3.1 electron volts, it's going to be transparent because the photons can't be absorbed. They can't make an electron jump to a higher energy state. So this equation was really, really useful to me in my research. Yes?
What happened to the other number, the other wave? Like, there was one, that one right there.
I just erased it and replaced it with 400 nanometers.
Okay.
Did a second calculation. So it's nothing special. So now the electromagnetic spectrum that we looked at back in chapter 24, we also have energy. So we have wavelength, energy, and frequency are all shown here. The frequency and energy have a one-to-one mapping because of that E equals HF. So if the frequency doubles, the energy doubles. The wavelength has the inverse relationship, so that's why you look at the markings and they don't all match up because of the inverse relationship. So we talk about visible light. We just calculated that the visible spectrum has on this side about 3.1 electron volts. On this side, it has a wavelength that's roughly twice that big, so half as big. So about, let's say, 1.6 electron volts for the red light. That's just an approximation. So that's the range of energies in the visible spectrum for a single photon. If you go to the beach, one of the things you should do is probably put on sunscreen. Why do you put on sunscreen? You want to absorb radiation. Specifically, what kind of radiation? Which kind? Ultraviolet. So ultraviolet, what is the energy of an ultraviolet photon? No, it's over the 3.1. Ultraviolet means above violet. We calculated that for blue or violet, it's about 3.1 electron volts. So anything with a photon energy above 3.1 electron volts is ultraviolet. You want that sunscreen to be absorbing those. Why? Because if you get much higher than 3, like if you get up to around 4 electron volts, that's enough energy for your skin to absorb the photon. What that means is you're going to have an electron that jumps up by that amount, and you're going to mess with the bonds of the molecules in your skin. You mess with the bonds and molecules of your skin, you can have things like the bond breaks. It reforms differently. Reforms differently is not good. Usually if it reforms differently, it's just going to be something that's incompatible. Actually, your body will usually fix it. But if your body doesn't fix it, it's going to be incompatible with life. It's going to die, goes away. But every now and then it's compatible with life and it exists. But now it's a mutant. Mutations are, well, they can be good, they can be bad. If they rapidly reproduce, what do we call it? Cancer. And so that's why you're wearing the sunscreen. It's to try to avoid the cancer that can occur because your skin absorbed the radiation, a bond got broken, it reformed incorrectly, and by some random chance, and the probability is very, very low. If the probability wasn't very, very low, we'd all just die from skin cancer. But every now and then it occurs that you form a mutation that's bad. Okay, that was all stuff that wasn't part of the lecture. Here's something that's part of the lecture, including a little zero that's not supposed to be there. I actually noticed it was there because my son wanted to. Oh, goodness. I have the wrong class. Give me a second. You guys are not in physical science class. I know this. Okay, you can answer now. What causes the characteristic peaks in an X-ray spectrum? All but one. Stop it, Alex. You changed your answer from right to wrong, though.
Go back.
There you go. That's better. Okay, now that Alex has fixed his. Okay, what causes the characteristic peaks? Alex, which one is it? A. Electrons falling to lower energy states. But we were spraying this thing with electrons. That's not what caused it. Which part of the X-ray spectrum was caused by the electrons that we were hitting our target with? I already answered this today. On a clicker question, even. What part of the X-ray spectrum was caused by the electrons that we were shooting at the target? Yes, I have this. Find a quick question. The what? Yeah, the first quicker question we had. This is the first one we had today? I thought we had one to start off with. Okay, then I'm just thinking back to the last class period. What causes, or what is caused by the electrons that we fire in? Okay, they're being accelerated, either slowed down or changing directions, and that causes the Bremsstrahlung, the radiation that's caused by accelerated charged particle. So electrons slowing down, not speeding up, but electrons slowing down is what creates the Bremsstrahlung or continuous spectrum. So that's what the electrons we are firing in are causing directly. But if an electron knocks a bound electron up to a higher energy state, then another electron in the nucleus can fall down, and that's what causes the characteristic peaks. Yeah, you're right. That is the first question. Duh, because I just restarted. Okay, now a second question. How's that? Which statement is true about wave theory? This is a question that we had when we started, well, actually just before we started talking about particle theory. Because I was going over this with my son and he had a missed idea. I have a wave traveling along and it goes from one material to another material. And I'm talking about the single wave going from one material to another material. Because he was just thinking, well, I can make a wave and I can do anything I want with that wave. But it's a single wave. Which one does wave theory say is true? It's supposed to, you're right. Pulling is closed, but it's supposed to be open. Sometimes okay, let me try it this way. It really doesn't want to answer. Okay, go ahead now. I am so sorry. Okay, we got 3 answers so far, so it's working. It didn't stop. You are already participating.
So I went to join the Photon.
Can you leave it? Try signing out and signing back in, maybe. I don't know.
I think I am signed out. I thought I was. Okay.
Hey, and you're in. Okay, just waiting on Christian. Okay, apparently didn't take it. There you go. Okay, so we have 113005. Which statement is true? Now this one here, we have a little more spread, but we do have a majority answer. Majority says the frequency of wave cannot change. Now, how can we have the frequency cannot change and the wavelength cannot change as 2 different answers? Because we have a relationship that says frequency is equal speed of light divided by wavelength. The answer A is the correct answer. The frequency cannot change in wave theory. You have a wave, remember I talked about having a string, 2 different kinds of string tied together. You have a wave that travels from one string into the next. It has to have the same frequency on both sides of the knot or the knot would have broken apart. So you have to have the same frequency on both sides. Frequency cannot change for a wave, according to wave theory. The wavelength then must change if the speed changes. Photon, no one answered the photon answers. Why? Yeah, photon is the name for the particle. You can't invoke the particle and say, yes, that's the wave theory. Right? If it's talking about the particle, it's talking about particle theory. So we have that one. Now, the follow-up question. Follow-up question is the same thing, but about particle theory, but it comes after we talk about Compton scattering. Arthur Holly Compton, in 1922, so this is, 17 years after Einstein came out with his paper, he was looking at light scattering, and he saw something weird. Now, you'll notice that this says the wavelength changed. He was firing photons, or let's say firing light, at a sample, and when he looked at the scattered light, he found that if it went straight through, there was no change at all. But if it was scattered at an angle, he actually had 2 peaks. The peak wavelength he fired in and a different one. Like I said, we just said wavelength can change according to wave theory. But this is all in air, so the speed of light is the same. If the speed of light's the same and the frequency and the wavelength changes, so does the frequency. So this was a measurement saying the frequency of the light changes on scattering. We just had a clicker question for the sole purpose of recognizing that's not allowed, according to wave theory. And so Arthur Holly Compton sees this, and of course it's shocking and baffling because wave theory says it can't happen, but there's a fallback. Einstein had come out with the photoelectric effect. He could treat the light as a particle when it's scattering. Basically, that's saying that instead of shooting a ray of light, we're going to shoot a beam of BBs. And when the BBs hit here, they bounce. Now, realistically, if I take this ball and drop it and it bounces, is it going to come back up and hit my hand? Why not? It's going to lose some energy. The energy is going to transfer into something else. And so if you treat the light as particles, then if its frequency drops, that just means that the photon lost some energy, transferred energy to something else. And so Compton was able to use relativistic calculations to show that his experiment actually agrees with light being a particle carrying energy HF, and when it bounces off an electron, it's going to transfer some energy and momentum to the electron, and so it bounces off with a lower energy. So which statement is true about particle theory now? So this is now going to particle theory. The same answers as before, but particles instead of waves. Ashley, Angelina, and Corso. Oh, and nice. All right. Our answers. 0, 0, 15. That's a 15. 3 and 1. No one answered A or B. Why not? Yeah, it said wave. Good job. I was hoping you would recognize that. 18 people answered one that had photon in it. One person was correct. If light is a particle, think of it like my ball. When my ball hits something, is its momentum going to stay the same? No. Is its energy going to stay the same? No. If you're going to treat light like a ball, like a particle, none of those are true. The energy can change, the momentum can change, they can all change. So the light says that we can change, or the particle theory says we can change all these things. So what Compton did is he sat down and he calculated, okay, so I have a photon coming in, it has energy equals HF equals HC over lambda, and then it's going to scatter. And so it comes off with energy prime is equal to HF prime is equal to HC over lambda prime. And the electron recoils with some energy of the electron. For conservation of energy, what equation can you make based on the symbols I have on the screen here? It's a very simple equation. We're not looking for anything complicated requiring significant knowledge. If energy is conserved, what does that mean? The energy we start with is equal to the energy we end with. That's what I heard from Ashley. That's going to have to be true. But that's not enough to solve this problem. It is a requirement to solve this problem, but it's not enough to solve it because there's also momentum involved. This electron initially had 0 momentum. It ends up with momentum that's non-zero. It's moving. That must imply that the photon had momentum as well. And so we have to go and say, what's the momentum of a photon? And so this is the equation that we just wrote down. Come on, where's the momentum of a photon? Here's the momentum of a photon. The momentum of a photon, it turns out, is its energy over c, hf over c, or h over lambda. And so we also have to have the momentum conserved. Now, momentum is a vector. So we're going to have momentum in the original direction the photon was traveling is conserved, and momentum in the direction perpendicular to that is conserved. And so using those equations for conservation of momentum plus the equation for conservation of energy, doing math that we are not going to do, right, here's the math that we're not going to do. This is conservation of momentum in the x direction and y directions. Arthur Holly Compton was able to calculate that the shift in wavelength is equal to Planck's constant divided by the mass of an electron times the speed of light. That factor out front, h, Planck's constant over MEC, is called the Compton wavelength. Times 1 minus cosine theta, where theta is the angle that it's deviated by. So going back to the picture, nope, don't have it there. Going back to the picture, here's the picture. Theta is the angle that the photon's direction deviated. So if the photon is undeviated, if it goes in a straight line, then cosine theta is going to be cosine of 0. Cosine of 0 is 1. And so there's going to be no wavelength shift if it goes in a straight line. If it reflects straight back, then theta is 180 degrees. Cosine of 180 degrees is minus 1. 1 minus a negative 1 is 2. And so the wavelength shift would be twice the Compton wavelength if it bounces straight back. Any other angle is going to be between those two. How big is that Compton wavelength? That Compton wavelength is 2.426 times 10 to the minus 3 nanometers. Now remember, visible light is 400 to 750 nanometers. So that's on the ballpark of 1/100,000th of the wavelength of visible light. That's a very small shift. You have to have very sophisticated equipment to measure that small of a shift. What would happen if instead of scattering off of an electron, it scattered off of a proton? Protons are much more massive. Notice the Compton wavelength was divided by the mass of the electron. So if you bounce off of the proton, what's that going to do to the wavelength? It's going to make it which way? Makes it smaller. It's going to make it much, much smaller. So a Compton scattering could occur from scattering off of a proton, but the shift for the proton scattering is so small that it's really not measurable. But we can measure it with visible light with sophisticated equipment. Using ultraviolet light or X-rays, it becomes easier to measure because the shift is a bigger proportion of the light that you sent in. Right? Because if you send in light that's 400 nanometers and you have a shift of 0.001 nanometers, that compared to the wavelength of light, that's a really tiny shift. So it's very hard to observe. So let's do a simple problem. An X-ray, using X-rays because of the short wavelength, has a wavelength of 10 picometers. What does pico mean? It's the minus 12. So my wavelength is 10 times 10 to the minus 12 meters. It's scattered through an angle of 110 degrees by an electron. So I have my photon comes in, it hits an electron, and the photon comes out like that. Deviated by that amount. And the question is, what's the kinetic energy of the recoiling electron? How can I determine the kinetic energy of the recoiling electron? Let's hear a process. Okay, we have initial energy of hc over lambda. What's the energy of this one here? What's the energy of the scattered one? That's right, hc over lambda prime. And then my electron, what direction is my electron going to go in this diagram? It's going to have to go forward and down because I need conservation of momentum in the horizontal and vertical directions. And I put E before I really should have put kinetic energy equals unknown. Using my energy balance, energy initial is equal to energy prime plus kinetic energy of the electron. So kinetic energy of the electron is equal to energy initial minus energy prime equals hc over lambda minus hc over lambda prime. What do I not have that I need to calculate? Lambda prime. And so for that, we use this number with this equation. So lambda prime is equal to lambda plus lambda Compton times 1 minus cosine of theta. I'm actually going to put in the numbers. So we have to put that cosine of 110 degrees, 1 minus cosine of 110 degrees. And my calculator is. Somebody else probably do it quicker than me. Is that the final answer? No. 1.34. So 2.426 times 10 to the minus 12 times that. Plus 10 to the minus 10 times 10 to the minus 12. So I get 13.256, all right? Times 10 to the minus 12 meters. Sorry. Sorry. Hey, it went away at least. So we'll put that right here. There's our calculation for the prime wavelength. And then we just put those in. I didn't do it. So we'll put those in here, and I'm just going to put, does it say an electron voltage? Does it say what unit? It doesn't say the unit, so I'm going to use 1240 nanometers times EV over 0.0100 nanometers minus 1240 nanometers times EV over 0.013256 nanometers. And that will give me my energy of the electron. We're out of time now, so I'm going to stop there. But that is an example of Compton scattering, which is, actually I'll stop there. I'll stop with this question, because this question is the important payoff for today's lecture. Which phenomena, multiple, plural, support a particle theory for light? So answer all that are correct, and like I said, it's multiple, and then hit enter. Okay. James, Amanda, Jeff, Erika, Angelina, Brandon. Okay, we're out of time, so we need to go, folks. Angelina. As she's answering, only one person gave an incorrect answer. There were 14 that said Compton scattering, 17 that said photoelectric effect, 14 that said X-ray, one person said Rayleigh scattering. Rayleigh scattering is the scattering that makes the sky blue. That is a wave scattering. So it turns out that we now have looked at actually more than two, a number of phenomena that say light is a particle, a number that say light is a wave. We have a contradiction, and the physics answer is light is both. It has both wave properties and particle properties. And so when you're looking at phenomena, you either use one or the other to explain it. All right, have a great day. I'll see you Friday.